This is Euclid Book 1, proposition number 35. And I'm sure you noticed in proposition number 34 that even though the two parallelograms were equal, they weren't exactly in the lines of lengths and widths the same size. So what was equal about them? And what's going to be equal with these? Well, it's not so much the lines that are going to be equal, it's going to be the area inside the parallelogram that's going to be equal. And that's what we're going to prove in this case. We're going to say that the area in this parallelogram is going to be equal to the area in this parallelogram. Now, how are we going to do this? Well, first of all, we have established we have two parallelograms. That means these two sides are going to be equal, and these two sides are going to be equal. This parallelogram is known as A, B, C, D. Okay? And this parallelogram over here is going to be known as E, F, G, and H. So these two sides are going to be equal, and these two sides are going to be equal. Let me move over here. These two are going to be equal, these two are going to be equal. Now, what we want to say is that this parallelogram here is equal in size to this parallelogram here. That means the same amount of area in here is the same as in here. How do we know this? Well, first of all, BC is equal to FG. So the length of BC is equal in size to the length of FG, which is right here. That is given to us. We are automatically told that the length of BC and the length of FG are the same. Alright, now, we already know that FG and EH, which is this length right here, and this length right here, these two lengths are equal because this is a parallelogram. Okay? So now, because we know that this length is equal to this length, and this length is equal to this length, then now we can say that BC is equal in length to EH because of the transitive property. Now, FG is parallel to EH, and that's because this is a parallelogram. Alright, BC is parallel to EH because of the transitive property. If this line is parallel to this line, and this then this line will also be parallel to this line. Okay? Now, we could also then say that EB is parallel and equal to CH. This is CH right here. So this line here is parallel to this line here. They're also equal in size, which means that we have a parallelogram, and it's called BCEH. This whole thing is a parallelogram. And that's by proposition 134. Now, EB is parallel to CH because of proposition number 33. So, Book 1, proposition 33 made these two lines parallel. Book 1, proposition 34 made this whole parallelogram a parallelogram. And now we go to proposition number 35, which says that parallelogram EBCH contains the same area as ABCD. Now, I know these lines are stretched out like this, but it doesn't matter. There is the same amount of area in this parallelogram as there is in this one. Okay? And because of that, because of proposition 135, since this parallelogram is equal to this parallelogram, and this parallelogram is equal to this parallelogram, then we can finally say that this parallelogram is equal to that parallelogram. And that's what Euclid was trying to prove. Alright, I will tell you more in a future video, so stay tuned.